Welcome to this lesson on angular momentum. As always, we will begin with a review of linear and angular. We started off with kinematics, distance, velocity, and acceleration, and their rotational equivalents of theta, omega, and alpha. Moving on to dynamics, we began with mass, which has its equivalents of moment of inertia, force with torque, work with rotational work, where work is force times displacement, and work in a rotational sense is torque times the change in angle. Linear kinetic energy, which was 1/2 mv squared, and rotational kinetic energy, which is 1/2 I omega squared. And now we transition to momentum, which has its rotational equivalent as angular momentum. If we recall, momentum is the product of mass times velocity. Doing our one-to-one substitution, instead of momentum, we get angular momentum, mass with moment of inertia, and velocity with angular velocity. In terms of units, moment of inertia carries units of kilogram times meter squared, and angular velocity of radians per second. When I reduce this, we get units of kilogram meter squared per second, which indicates that angular momentum is in and of itself its own quantity, because momentum carries units of kilograms meters per second, whereas the angular momentum has the meter squared, so they are different units. If I recall, momentum is mass times velocity. The momentum has a vector quantity in the direction of the velocity and is the product of the two things. If I look at an object rotated through its center with a moment of inertia I and rotating at angular speed omega, it is said to have angular momentum L, which again is equal to the product of I times omega. But what is the direction of this angular momentum? For that, we need to use the right-hand rule. Let's look at a similar cylindrical object rotating at angular speed omega. In order to determine the direction of its vector momentum, we need to use the right-hand rule, which says we take our right hand and we place our right hand on the object so that our fingers curl towards our palm in the direction of rotation. It is then said that the angular momentum or the angular velocity vector will be perpendicular to the direction of rotation along our thumb, L. This must be done using the right hand. So going back to our example, the angular momentum vector will be along the axis perpendicular to the rotation, directed outward, L. Take a moment to pause and practice this with your right hand so that you can see your thumb will point in the direction of the angular momentum. Next, we discuss conservation of angular momentum. Much like linear momentum, angular momentum is also conserved and is the third and final conservative law of honors physics. Angular momentum says that L initial equals L final, which means in magnitude, I initial times omega initial has to equal I final times omega final. Let's demonstrate this. In this scenario, I rotate with my arms and legs out, tuck them in, and what you notice is my rate of rotation changes. Taking a look at myself on the stool, drawing an axis through my center, we can see that my mass is out at a larger radius, giving me a moment of inertia generically as the sum of each piece of mass times a radius squared. When I tuck in, that same mass is at a much smaller radius, therefore giving me a smaller moment of inertia, so that the initial moment of inertia is greater than the final moment of inertia. So when I look at this in magnitude, in terms of conservation of momentum, I have a large I initial to begin with, as we illustrated in this example, and a small angular velocity. On the other side, I brought my arms and legs in, reducing my moment of inertia, and as a consequence, my final angular speed increased, therefore demonstrating conservation of angular momentum, as those two quantities will always be equal in magnitude and direction.